Welcome back to our video lecture in ENSC 107, and in this video we will start a new topic on pressure and hydrostatic equations. Pressure and temperature, they actually affect other properties of fluids such as the density and the viscosity. Okay, so they're actually a property also. The reason why it deserves a lecture discussion, just focus on pressure, it's because the succeeding topics, or let's say other topics, actually depended or depends on this topic. Okay, so first let's define what is pressure. Okay, so pressure, it is defined as the amount of force exerted, or I used to call it a force distribution over a unit area. And this unit area is actually perpendicular to the direction of the force. Okay, so if we try to illustrate it here, so let's say a heavy surface, a curved surface, and if we take an infinitesimal area, we have forces that's perpendicular to the surface, to this unit area. Right? So it's always perpendicular. Okay, so mathematically, pressure is expressed as force over area. Okay, and the unit of force is in, let's say in metric, that's Newton, and the area is in meters squared. And this Newton per meter squared gives the derived unit called pascals, or PA. Okay, so that's pressure, force over area, and in English systems, it is PSI. That's just pounds per square inch, right? So this is the unit of area in the English systems, and this was the pound force per area, or the shortcut is PSI. Now, if we are asked to find the pressure at a point, so again, let's say pressure at a point, it's we can think of it as or about the infinitesimal area. Okay, so if we take a limit of this, let's say the pressure, if we take the limit of the area, delta F over delta A, as delta A approaches zero, so that would result to a derivative. So that's dF all over dA. Whereas this one is an average value, and this one is a derivative value, instantaneous values. Okay, so another notes on pressure is that pressure often varies from point to point. Okay, from point to point in space, and that pressure is a scalar quantity. When we say pressure is a scalar quantity, it means that the it's not about, or it does not concern itself about the direction, right? So we can just write it's not about directions. Or you can say what matters is just the magnitude. Okay, so it's simply because it's always perpendicular to the air. Okay, so question. What's the difference between pressure and stress? So pressure versus stress, what's the difference? All right, let's give a trivia here. Trivia, what is the difference between pressure and stress? If you notice that pressure is, the unit of pressure is Newton per meter squared. The stress is the same, right? That's Newton per meter squared, or let's say pascals. But what is the difference? Pressure is also a force distribution of an entire area. This one is a force distribution as well. But are they the same thing, or are they the same units? The answer is no. Why? Because pressure, this is external, whereas stress is internal. Now think, for example, a rubber tire for the wheels. Let's say this is a wheel, the rim of the wheel, and then this one is the rubber tire where you inflate it with air. Okay, so as you introduce air here, so there's going to be pressures, right? And we say that pressure is perpendicular to the area. Okay, so here as well, there's going to be pressure. So as you can see that pressure is external, but if we are trying to find the strength of the materials, let's say the rubber itself, will the thickness of the rubber be able to withstand the pressure? Then the stresses inside, so let's say this is a rubber, the cross section of the rubber, right? And here, these are the pressure or the force distribution external to the tire material. And if we want to check the force distribution inside here, the forces, the internal forces, then that's what we call stress, right? So this one is stress is internal, whereas this pressure is external. Okay, so I hope this solves confusion regarding this pressure and stresses. Okay, so the next thing that we'll talk about is that there are two important properties, or rather two important principles, right? Two important principles about pressure. Okay, so based on I think that's from the findings of Blaise Pascal's. So the number one, it says that pressure acts uniformly in all directions on a small volume of fluid. The number two, in a fluid confined by solid boundaries, pressure acts perpendicular to the boundary. Perpendicular to the boundary. Okay, so these are the two important principles about pressure. Now what it says here in number one, it says that pressure acts uniformly in all directions on a small volume of fluid. Okay, so imagine that we have this region or space Okay, so this is space x, y, z. Now, if this is a region of space wherein that space is filled with a fluid, then if we take a volume, a small volume, or a differential volume, or what they say pressure at a point, then this small volume experiences pressure in all directions. So meaning it has a pressure on the x, along the y-axis. It has a pressure along the z-axis, and then the y-axis, and as well as the x-axis. Right. So let's say we have a lot of it's a continuum, right? So at every point in space there is a matter. There's no discontinuity in this space filled with fluids. Okay, so that's number one. And in number two, it says in a fluid confined by solid boundaries, pressure acts perpendicular to the boundaries. Now it says here in number two that, for example, you have a solid boundaries, something like this, right? So I still want to draw this in 3D, in three-dimensional. So for example, these are our x, and this y and z. Then if there's a presence of a solid surface, or let's just write a curve here, let's draw a curve surface here, so that's gonna be perpendicular. Right, so this fluid will exert forces on this solid surface that's perpendicular, right? Okay, so the application is that for example, if we are going to design a pipe that will be used for conveying a fluid, then that pipe has to be able to resist the pressure, right? So if we draw the cross section here, we have pressures from the fluid, so it exerts pressures. Okay, so the material, or the pipe material, must be able to withstand the pressure that it will carry, otherwise the material will fail. Another one is storage, let's say storage tanks. Okay, so let's say in storage tanks, they're actually, or they are commonly found in processing industries, food industries. So if you fill this storage tank with fluid, let's say a liquid or something, some foodstuffs here, liquid foods, so there's actually a pressure from the fluid. It induces pressure on this tank wall, and this tank wall must be able to withstand the pressure. Now how much more if it's a pressurized vessel, right? Okay, another example or another application is in the design of dams. So the design of dams, you're actually storing storing your water by just putting a dam right here, right? So let's say this is the left side, and then the right side, this is the water level, this one is the water level. Now on that dam material, of course, there's going to be pressures right here. Okay, so right here as well, and I purposely draw this pressure distribution, or force distribution, that's something like this, and the reason for that is later on we will derive the equation called the hydrostatic equation. Okay, so now let's move on to the different scales or measurements. When I say measurements, I mean different ways to define the pressure, or to measure the pressure. Okay, and that's the topic on absolute, right, gauge, and atmospheric pressure. Okay, so before we can measure, we need to understand the references or the reference point from which we measure the atmosphere. From which we measure the pressure. Okay, so we have this absolute pressure. Okay, so when we say absolute pressure, we mean that it's, the pressure there is zero. So zero pressure, and it's a reference point. Reference point where pressure is zero. And when we say atmospheric pressure, it's also a reference point, and usually the value of this is based on the sea level, and we have this value 101.3 kPa, and that's at sea level, or in psi, if I remember it correctly, that's 14.7 psi at sea level. Okay, so depending upon your atmospheric condition or the ambient space, then this pressure, well, this reference point would also change. Okay, so if this is a sea level, then let's say this is the sea level, and we have this. And your location is, let's say, 100 meters above, right? So this is, right, let's say this is me. Now, if I have a location of, let's say, 100 meters above sea level, then of course the pressure right here would be different from, the atmospheric pressure at this point would be different from the atmospheric pressure at this point. Yeah, however, if the difference is not much significant, and sometimes for calculation purposes, because we don't have data at this point, then we can just, for computation purposes, we just use the value here, the pressure at this point, which is 101.3 kilopascals or 40.7 psi. But here, we don't know actually. Maybe it's close, maybe it's not. So that depends upon your elevation from this reference point. Okay, so again, there are three measurements, or three types of pressure measurements, and it's absolute pressure, where the reference, where the pressure is zero. Then we say the atmospheric pressure, and that's based on some data that's already been established, and we have this data 101.3 kPa at sea level, or 40.7 psi. That's the atmospheric pressure, which is also a reference point. Okay, so now when we say gauge pressure, it's a pressure that's measured relative to the atmospheric pressure. Okay, so now if we try to draw here, let's say this is the absolute pressure line. So the pressure right here is zero. And if we have right here another reference line, that's the atmospheric pressure. So the pressure right here is 101.3 kPa or 40.7 psi. Now, if we measure from this line to somewhere, let's say it can be positive or negative. Now, this measurement is what we call the gauge pressure. Now, it can be positive or it can be negative. Oftenly, when they say negative, they also refer to that as the vacuum pressure. And take note that this vacuum pressure, it's negative with respect to the absolute pressure, I mean to the atmospheric pressure line only. Okay, so if we tabulate this, or if we write down the relationship between the three pressures, we have P absolute is equal to P atmospheric plus the P gauge. All right, so for example, if I am trying to find the pressure at this point, then it can be that this one is the P gauge, right? P gauge, and from this point to this point, that's P atmospheric, ATM. So therefore, from this reference line to this point, that's what you call the absolute. Okay, so let me write it again. We have this reference line, the absolute, P abs, and then this one P ATM. So if we have this, if we want to determine the pressure at this point, then from this P atmosphere to that one, that's P gauge. And from this point, from this reference line, from zero line up to here, that's P atmosphere. So therefore, if we base our pressure measurement from the absolute line to this point, that would be P absolute. Okay, so now let's tabulate it. Now we have the SI, then we have the English units. Now for P abs, our SI unit is kPa, but here we have PSIA. And then here we have P atmospheric. This one is in kPa, still in kPa, but this one is in PSI. And for P gauge, this one is still in kPa, but in the English unit, that's PSIG. Okay, so I guess let's try to solve some problems here regarding let's try to solve this one. The problem number one, it says express a pressure of 155 kPa gauge as an absolute pressure. The local atmospheric pressure is 98 kPa. Okay, so for problem number one, it says we have to convert. We are given a P gauge of 155 kPa and a P atmospheric equal to 98 kPa. Okay, so therefore P abs is just simply P atmospheric plus P gauge. That's equal to 155 plus 98, which is just 253 kPa. Okay, number two, let's try this one. Number two, express a pressure of 225 kPa as a gauge pressure. So it says here, this is absolute pressure. The local atmospheric pressure is 101 kPa. So that would be, say here, P abs is 225 kPa and P atmospheric is 101 kPa. So therefore, if you express this in terms of P gauge, so we just have P abs. This is just very basic computation plus P gauge. So P absolute minus P atmospheric is equal to P gauge. So therefore, P gauge is equal to 124 kPa. Okay, now let's do this. Another example problem. Express a pressure of 10.9 psia as a gauge pressure. The local atmospheric pressure is 15.0 psia. Okay, so meaning that this atmospheric pressure is based on the absolute pressure line. Okay, so you just have to. Okay, so our P absolute is 10.9 and psia, and our P atmospheric is 15 psia. So therefore P absolute is equal to P atmospheric minus or plus P gauge, right? So P gauge is just equal to P absolute minus P atmospheric. Our P absolute is 10.9 minus 15. That would result to negative 4.1 psig. Okay, so the meaning that we are lower than the atmospheric line, so this is a vacuum pressure actually. So recall this is our P, let's say this is our P atmospheric, and it says that our absolute is 10.9, and we have an atmospheric pressure of 15. So from this pressure line up to here, right, so this will be our gauge pressure. That's negative 4.1 psig. All right, now we'll I think we'll start the next section of the topic, which is the hydrostatic equation. I guess we'll just continue, we'll just start it in the next video.